So before we move on, let's talk some more about the gradient calculation here, because this is a key component of deep learning. So and when discussing logistic regression, we introduced an approach to supervised learning based on gradient descent. Essentially, we calculate the gradient of the loss function with respect to the weights, and then adjust the weights along the gradient direction to reduce the loss. Now, we will apply the exact same approach to learning the weight in a neural network or in a computation graph. So for the weights leading into the output layer, so the last layer before the y hat, there's no problem, because we can just get the gradient essentially by taking the partial derivative of y hat with respect to each one of those last layer weights. However, for weights leading into the hidden layers, like W1 and W13, W14, and so on, which are not directly connected to the output, the process will be more complicated. So, like we said, for now we will use the same loss function we used before, which is the L2 loss function, and try to calculate the gradient of this L2 function with respect to the weights for a single training example. But of course, once we found a way to do it for one training example, we can repeat that using vectors and matrices for all training examples. So the network output prediction is y hat, and the true value is y, and we said the loss function would be y minus y hat squared. Now, to compute the gradient of this loss function with respect to the weight, we're going to have to use the chain rule, exactly like we did with logistic regression. Essentially, we'll start with an easy case, for example, W3 and 5 that is connected to the output unit. So if you look here, W3, 5, this is connected to the output. So there's no problem really getting the derivative of the loss function with respect to this weight, because there's no need for any chain rule in this case, right? We can just say the partial derivative of the loss function with respect to W35 is the partial derivative of y minus y hat squared, which is essentially negative 2 y minus y hat partial y partial W35. And simplify the process, simplify the result. Now, the more difficult case is getting the derivative of the loss function with respect to these weights, the hidden layer, W13, W23, and so on. So here we have to apply the chain rule. Essentially, first we have to get the derivative with respect to this weight, and then use the chain rule to link this derivative to the derivative with respect to the weights we're interested in. Okay, and by repeating this process, we end up with symbolic formulas essentially for the derivative of the loss function with respect to each weight in the layer. This process we just did by going backward from the output all the way to the input layer is called back propagation. Okay, because essentially we're back propagating the error at the output back throughout the network. So an important characteristic of these gradient expression is that they have as factors the local derivative. So they will always include the derivative of the activation function with respect to their input. And that's why for all the activation functions that we discussed, the derivative is must be clearly defined. Okay. So as you can see, the derivative in that case in all these functions are always non-negative, but they can be very close to zero, especially in the case of sigmoid and 10H activation function. or exactly 0 in the case of the redo function. So if the derivative of a given activation function g prime is small or 0, that means that changing the weights leading into j will have almost no effect on the loss function. As a result, then, deep network, if you make your network very deep, they will suffer from what is called vanishing gradient, which is essentially by the time your backpropagation reaches the earlier layers, the derivative will be so small that no matter what you do for the weights of these earlier layers, you're not going to be able to change the outcome of the network. So the error signals essentially are extinguished altogether as they are propagated back through the network. Okay. Now there are solutions to the vanishing gradient problem to be able to still calculate the gradient with respect to weights early in the layer. So as you can see then, the gradients in this tiny example will be symbolic expressions that will be computed by passing information back through the network from the output units. So it turns out that this property for this simple network is actually holds for much deeper networks. Okay, so the gradient computations for any feed-forward computation graph have the same structure as the underlying computational graph. Okay, so this is how we're going to then calculate the gradient, and you will not have to do any of these calculations, obviously, when you build your networks, because they were all, of course, in packages like TensorFlow and PyTorch, and they're all computed for us. Okay, so all of the major packages for deep learning, of course, provide automatic differentiation so that you as a user can experiment freely with different network structures, activation functions, loss functions, and not worry about deriving a new way to get the derivative of the loss function with respect to the weights. So this is essentially an approach called end-to-end learning, in which complex computational system for a task such as machine translation can be composed from many trainable subsystems, and the return system is then trained in an end-to-end fashion from input to output. So with this approach, you as a designer of the machine learning or the neural network, you don't have to really be an expert into how the overall system works and how the derivatives are calculated and so on. But all you have to worry about is how to architect, how to structure or design your network in order to complete the task you're looking for. Next, we want to talk about input encoding. So we already established the basic idea for deep learning. We said that we represent hypotheses as computational graph with weights that will be tuned, and essentially we're going to use back propagation to compute the gradient of the loss function with respect to each one of these weights in order to improve the fit of the network prediction to the training output, the training data. Now we look at how to put together a computational graph. We begin with the input layer, which is where the training example x vector, regardless of how many inputs we have, is encoded as values of the input nodes. Then we consider the output layer, where the outputs y hat, as we call them, are compared with the true value y to derive our loss function, which will then allow us to tune the weights. And finally, we will look at the hidden layer. So the first step is to encode the input. So the input and output nodes of the computational graphs are the ones directly connected to the input data X and the output data Y. The encoding of input data is usually straightforward, at least for the case of factored data where each training example contains values for a number of attributes. Let's call it n. Now, if the attributes are Boolean, then we have n input nodes, usually 0 and 1. So 0 is false and 1 is true. Sometimes we use negative 1 to 1. Now, numeric attributes, if they're, say, for example, square footage, if we're working on a house price prediction problem, anything like that, or number of bedrooms. So regardless, it's integer or real values, we can use them as is, okay? Although they may be scaled to fit within a range. So it's always a good idea to standardize your input using the mean and standard deviation for each input feature to make sure that the design space for each input is similar. Okay, you don't want an input measured in the thousands and another one measured in the one and so on, because as you'll see, this will affect the convergence of your training algorithm, because the gradient will reflect these values. So it's always normal practice to use standardization to standardize all the inputs, numeric inputs. So this way, if you have magnitudes for that vary in a very wide range, they are mapped into a more normal range, like mean and two standard deviation, for example. What if the input is an image? Okay, so if the input is an image, so what do we use then? We could use, the X by Y pixels, right? We have 3 values for each pixel, red, green, and blue. And then we can say then if I have X times Y number of pixels and 3 values for each pixel, then that gives me 3 times XY integer values that I can use as my input vector. But this would then ignore the fact that RGB triples belong to the same pixel in an image, and the fact that pixel adjacency really matters, right? If you just unroll the entire image into one very long vector, then you lost this information that pixels next to each other are related, and that each 3 values belong to a single pixel. Now, we could map adjacent pixels into adjacent input nodes in the network, but the meaning of adjacency is also completely lost if the internal layers of the networks are fully connected. So, in practice, networks used with image data will try to capture this information, as you will see later on in convolutional neural network. Okay, let me continue the next piece.